If we think of the Grand Canyon's glassed-in hoop structure, that's what's called a cantilevered beam. The idea is that it's supported at one end, and we actually enforce that the slope be 0 at this end as well. So it has to come in flat, and then it might bend afterwards like that. But we know where the position is, and we know what the slope is at the beginning. We'll take a simple example here of a 2x4, so something you can buy at your local retail store. It'll be 2 meters long, and based on that 2x4 structure, there's a certain moment of inertia for the cross section, and this is for pine. It's the modulus of elasticity, and these are just the building blocks we need to build our solution. What we're going to do is apply a 100 Newton per meter force. So this whole distance here is going to be 2 meters long. We're going to apply a uniform load, which is for each meter is going to be 100 newtons. And if you think about what that means, gravity's being about 10 meters per second squared, that's like applying 10 kilograms to the left and to the right meter here. So that gives you a perspective on how much weight we're talking about. What we'd like to do is find the amount of deflection at the tip. So we know when we apply this load, this part here is anchored, so the beam is going to bend down. And what we want to know is, what is the deflection? How far away has that tip moved from just being a straight beam? Well, to find that out, we're going to need our initial conditions and our differential equation. So the initial condition here describes the position, so y will set at 0 at the origin. We'll also set the slope to be 0, so it comes out straight at the beginning anyway, so the slope here is flat. These other two conditions are boundary conditions. These are at the tip. Notice the 2 inside here. What we can say at the tip is that there's going to be no curvature, and you get some technical reasons for why this third derivative is 2. Suffice it to say that these would be provided to you. You would not be asked to generate these boundary conditions for this particular structure. However, once they're given, we can see what kind of result we get. We recall that our differential equation is EI fourth derivative equals P of x, but P of x is just a constant now. It's 100. We've already determined that the complementary solution is C1 plus C2x plus C3x squared plus C4x cubed. And now we have the question of our differential family to find our y solution to the non-homogeneous version. Well, the differential family is just a constant. So how does that play out? Well, what we'd usually do is assume that our solution for the non-homogeneous part would be a constant as well, except that is already in our corresponding solution, our complementary solution. It's right here. Well, what should we do next? Well, we would multiply this by x until it becomes not in our YC. We multiply by x, well, that's there already. Multiply by x again, that's there already. Multiply by x again, that's there already, until we get x to the power of 4. So we look at our right-hand side, we see it's a constant, but constants are in the solution. Multiply by x, still in the solution. Multiply by x, still in. Multiply by x, still in. Multiply by x, we're outside our YC, and now we have a plausible solution that might account for this non-homogeneous part, and we'll see how that works out in the next page. So our proposed solution is a times x to the power of 4, and we're going to sub that into the differential equation and solve for a. Well, to be able to achieve that, we need to have the fourth derivative available. So let's take a whole bunch of derivatives here. Fortunately, these are nice, simple derivatives. Keep taking more derivatives. We need the fourth derivatives. This is the highest order we've dealt with in an application. And I'll bring the 3 down. And third derivative is going to be 24a times x. And the fourth derivative will simply be 24a. When we put all these into the differential equation, well, it turns out only one of them is needed, this fourth derivative. So we'd have ei times 24a equals 100. So a is equal to 100 over 24 ei. That means our solution that corresponds to the non-homogeneous part would be 100 over 24 ei times x to the 4. So we just found the A value in this term, and we're subbing it in and completing the solution there. And that gives us the general solution then, which is y equals c1 plus c2x plus c3x squared plus c4x cubed plus this value here, 100 over 24 EI times x to the power of 4. Again, it's just the combination of our yc plus our y for the non-homogeneous part. What we can say there is that the deformation of the beam will follow this fourth order polynomial regardless of the boundary conditions, but now we're going to use the boundary conditions to identify the values of C1 through C4, and that will actually give us then at the end a prediction of the shape of the beam and therefore a prediction of how much deflection there will be at the tip. So we have y of 0 equals 0. If we sub 0 in for x, the only thing left standing is going to be C1. And so C1 will equal 0. For y prime of 0, we're going to need y prime. That will be C2 plus 2c3x plus 3c4x squareds, and then the derivative here, plus 4 times 100 over 24 EI x to the 3. When we sub in the value of x equals 0, y prime equals 0, we're going to have 0 equals c2, and that's our second constant. Now to find c3 and c4, we have two further conditions we can use. These are at the tip though. We'll see the math works out a little less nicely because we're not using 0 as our x value, but it is still straightforward for this application. I've rewritten our solution here in the simpler form, having already seen that c1 was equal to 0 and that c2 is equal to 0. There's only 3 terms left after that. We took the derivative earlier. Here it is. We're going to need the second derivative to be able to use these conditions. So let's compute that by taking a derivative. And we get 2c3s plus 6c4x plus 12ax squared. And I just left the a as this combination here. It's a little less messy if we keep it as a letter rather than that complicated expression over there. We're also going to need the third derivative, so we might as well take that right now. That would give us 6c4 plus 24a times x. Then we use our second derivative at the end, has to equal 0. So that gives us 0 equals 2c3, and our x value here is going to be 2. So that's the important difference here. That gives us 12 C4s plus 4 times 12 is 48 A's. And that's the constraint on C3 and C4. There's also the other condition, the third derivative has to equal 0. And that gives us 0 equals 6C4 plus 24 times A times 2. That'll be 48A as well. From this stage here, what we would like to do is solve for C3 and C4. Well, C4 is right here, so we can actually get it fairly quickly. C4 times 6 is going to equal negative 48A. We'll divide by 6, and we will get negative 8A. And our C3 then can be obtained from the earlier equation. C3 will be 1/2 of minus 12 C4s minus 48 A's, and that will be minus 6 C4s minus 24 A's, or minus 6 times minus 8A minus 24A. That's 48 minus 24. That'll be positive 24 A's. So our y is going to equal 24 A's, C3, times x squared, plus our C4, which was negative 8 A's, plus an A times x to the 4. And we know again what A is, so that's fine. What we were asked for was the deflection at the tip. Well, the deflection at the tip, that's equal to the y of 2. What is our actual coordinate of the beam at x equals 2? Going back to the picture, we know what the initial conditions were at x equals 0, and then what we want to do is sub in x equals 2 to find out the position there. So we simply find out what y of 2 is. That'll be 24a times 2 squared minus 8a times 2 cubed plus a times 2 to the 4. And using the value of a up here and the two values of I and E that were given to us, which are related to the 2x4 material and cross-section, we'll end up with 48 A's, and 48 A's will give us 0.00986. Now, what are the units here? All the units we used so far were meters, so this is meters, or if you want the real translation here, this is very close to 1 centimeter. What that describes is, if we had the beam without load here, 2x4, 2 meters out, and we apply this load, what we actually get is a bit of curvature, so it deflects, and the deflection at the end is going to be 1 centimeter down from a straight line. Now that might not seem like much, but if you've ever built a floor, if it went down by 1 centimeter when we applied such a small load, a total load of 20 kilograms is all we used here, that would be a cause for concern. You definitely would not want to build that Grand Canyon cantilevered structure out of 2x4s. Let's turn this around for a second and note the structure that we had before. We found that y of 2 at the end of the day was going to equal 48a, and a equaled 100 over 24 EIs. Well, that 100 was exactly what we had as our load per meter. And so if we wanted to reduce the deflection, it turns out it's as simple as modifying our A value here. We want this value, the deflection, to be less than 2 millimeters. So we'd say, well, we can have 0.002 meters, because those are the units of our calculation. And that would equal 48 times A, which is P over 24 EI. Solving for P, we get P equals 0.002 times the 24 EIs all over 48. And that gives us around 20.3, and the units of force here were newtons per meter. Notice we start off with 100. To get down to this value, we'd have to scale by, not surprisingly, a factor of about 5. To quickly recap, the beam example is interesting in its own right because it's a very common engineering task and it has interesting mathematics in it. The mathematics in particular, because the equation is so simple, it gives us this almost too simple result for the characteristic equation, and we really have to rely on that procedure for handling multiple solutions of the same type, both within the corresponding solution and within our guess at the non-homogeneous part, which might also overlap with the corresponding solution. So there's some neat math and some neat physics involved with all of this.